Slow-scan television is a picture transmission method used mainly by amateur radio operators to transmit and receive static pictures via radio in monochrome color. A technical term for SSTV is narrowband television. Analog broadcast television requires at least 6 MHz wide channels because it transmits 25 or 30 picture frames per second. But SSTV usually only takes up to a maximum of 3 kHz of bandwidth. It is a much slower method of still picture transmission, usually taking from about 8 seconds to a couple of minutes depending on the mode used to transmit one image frame. Since SSTV systems operate on voice frequencies, amateurs use it on shortwave, VHF and UHF radio. History. Concept. The concept of SSTV was introduced by Copthorne MacDonald in 1957-58. He developed the first SSTV system using an electrostatic monitor and a Vidicon tube. In those days it seemed sufficient to use 120 lines and about 120 pixels per line to transmit a black and white still picture within a 3 kHz phone channel. First live tests were performed on the 11-meter ham band, which was later given to the CB service in the US. In the 1970s, two forms of paper printout receivers were invented by hams. Early usage in space exploration, SSTV was used to transmit images of the far side of the Moon from Luna 3. The first space television system was called Seliger-Traldi and was used aboard Vostok. Vostok was based on an earlier videophone project which used two cameras, with persistent Li-23 iconoscope tubes. Its output was 10 frames per second at 100 lines per frame video signal. The Seliger system was tested during the 1960 launches of the Vostok capsule, including Sputnik 5, containing the space dogs, Belka and Strelka, whose images are often mistaken for the dog Laika, and the 1961 flight of Yuri Gagarin, the first man in space on Vostok 1. Vostok 2 and thereafter used an improved 400-line television system referred to as Topaz. A second-generation system was introduced after 1975. A similar concept, also named SSTV, was used on Faith 7 as well as on the early years of the NASA Apollo program. The Faith 7 camera transmitted one frame every 2 seconds. The Apollo TV cameras used SSTV to transmit images from inside Apollo 7, Apollo 8, and Apollo 9, as well as the Apollo 11 lunar module television from the Moon. NASA had taken all the original tapes and erased them for use on subsequent missions. However, the Apollo 11 tape search and restoration team formed in 2003 tracked down the highest quality footage among the converted recordings of the first broadcast, pieced together the best footage, then contracted a specialist film restoration company to enhance the degraded black and white film and convert it into digital format for archival records. The SSTV system used in NASA's early Apollo missions transferred 10 frames per second with a resolution of 320 frame lines using less bandwidth than a normal TV transmission. The early SSTV systems used by NASA differ significantly from the SSTV systems currently in use by amateur radio enthusiasts today. Progression. Commercial systems started appearing in the United States in 1970, after the FCC had legalized the use of SSTV for advanced-level amateur radio operators in 1968. SSTV originally required quite a bit of specialized equipment. Usually there was a scanner, a camera, a modem to create and receive the characteristic audio howl, and a cathode ray tube from a surplus this radar set. The special cathode ray tube would have long persistence phosphors that would keep a picture visible for about 10 seconds. The modem would generate audio tones between 1200 and 2300 Hz from picture signals, and picture signals from received audio tones. The audio would be attached to a radio receiver and transmitter. Current systems. A modern system, having gained ground since the early 1990s, uses a personal computer and special software in place of much of the custom equipment. The sound card of a PC, with special processing software, acts as a modem. The computer screen provides the output. A small digital camera and digital photos provide the input. Modulation. SSTV uses analog frequency modulation, in which every different value of brightness in the image gets a different audio frequency. In other words, the signal frequency shifts up or down to designate brighter or darker pixels, respectively. Color is achieved by sending the brightness of each color component separately. This signal can be fed into an SSB transmitter, which in part modulates the carrier signal. There are a number of different modes of transmission, but the most common ones are Martin M1 and Scotty S1. Using one of these, an image transfer takes 114 or 110 seconds. Some black and white modes take only 8 seconds to transfer an image. Header-A calibration header is sent before the image. It consists of a 300 millisecond leader tone at 1900 Hz, a 10 milliseconds break at 1200 Hz, another 300 millisecond leader tone at 1900 Hz, followed by a digital viz code identifying the transmission mode used. The viz consists of bits of 30 milliseconds in length. The code starts with a start bit at 1200 Hz, followed by 7 data bits. An even parity bit follows, then a stop bit at 1200 Hz. For example, the bits corresponding the decimal numbers chapter 44 or 32 imply that the mode is Martin M1, whereas the number 60 represents Scotty S1. Scanlines. A transmission consists of horizontal lines, scanned from left to right. The color components are sent separately, one line after another. The color encoding and order of transmission can vary between modes. Most modes use an RGB color model. Some modes are black and white, with only one channel being sent. Other modes use a YC color model, which consists of luminance and chrominance. The modulating frequency changes between 1500 and 2300 Hz, corresponding to the intensity of the color component. The modulation is analog, so even though the horizontal resolution is often defined as 256 or 320 pixels, they can be sampled using any rate. The image aspect ratio is conventionally 4:3. Lines usually end in a 1200 Hz horizontal synchronization pulse of 5 milliseconds. In some modes, the synchronization pulse lies in the middle of the line. Modes. Below is a table of some of the most common SSTV modes and the differences. These modes share many properties, such as synchronization and/or frequencies and gray color level correspondence. The main difference is the image quality, which is proportional to the time taken to transfer the image, and in the case of the Avt modes, related to synchronous data transmission methods and noise resistance conferred by the use of interlace. The mode family called Avt was originally designed by Ben Blish for a custom modem attached to an Amiga computer, which was eventually marketed by AEA Corporation. The Scotty and Martin modes were originally implemented as ROM enhancements for the Robot Corporation SSTV unit. The exact line timings for the Martin M1 mode are given in this reference. The Robot SSTV modes were designed by Robot Corporation for their own SSTV unit. All 4 sets of SSTV modes are now available in various PC resident SSTV systems and no longer depend upon the original hardware. AVT. AVT is an abbreviation of Amiga Video Transceiver, software and hardware modem originally developed by Black Belt Systems around 1990 for the Amiga home computer, popular all over the world before the IBM PC family gained sufficient audio quality with the help of special sound cards. These AVT modes differ radically from the other modes mentioned above, in that they have no per-line horizontal synchronization pulse but instead use the standard vis vertical signal to identify the mode, followed by a frame-leading digital pulse train which pre-aligns the frame timing by counting first one way and then the other, allowing the pulse train to be locked in time at any single point out of 32 where it can be resolved or demodulated successfully, after which they send the actual image data in a fully synchronous and typically interlaced mode. Interlace, no dependence upon sync, and interline reconstruction gives the AVT modes a better noise resistance than any of the other SSTV modes. Full-frame images can be reconstructed with reduced resolution even if as much as 1/2 of the received signal was lost in a solid block of interference or fade because of the interlace feature. For instance, first the odd lines are sent, then the even lines. If a block of odd lines are lost, the even lines remain, and a reasonable reconstruction of the odd lines can be created by a simple vertical interpolation, resulting in a full frame of lines where the even lines are unaffected, the good odd lines are present, and the bad odd lines have been replaced with an interpolation. This is a significant visual improvement over losing a non-recoverable contiguous block of lines in a non-interlaced transmission mode. Interlace is an optional mode variation, however without it, much of the noise resistance is sacrificed. Older computers sometimes needed to do this in order to make up for an inability to precisely match the synchronous timing of the frame over long periods. The AVT modes are mainly used in Japan and the United States. There is a full set of them in terms of black and white color, and scanline counts of 128 and 256. Color bars and grayscale bars may be optionally overlaid top and/or bottom, but the full frame is available for image data unless the operator chooses otherwise. Frequencies using a receiver capable of demodulating single sideband modulation SSTV transmissions can be heard on the following frequencies. Media in popular culture. The video game portal. In an internet update of the program files 3 years after its original release provided in-game radio objects, whose sound effects became part of an alternate reality game-style analysis by fans of the game hinting at a sequel of the game. The effects included Morse code strings that implied the restarting of a computer system, and could be decoded as SSTV images from a grainy video. These images included further hints of a BBS phone number that, when accessed, provided a large number of ANSI-based images relating to the game and its potential sequel. The sequel, Portal 2, was later confirmed. In the aforementioned sequel, Portal 2, more SSTV images are broadcast in RAM and DENS. When decoded, these images are pictures concerning elements of the game, such as the weighted companion cube on the moon, and slides with bullet points on how the alternate reality game was done and what the outcome was, such as how long it took the combined internet internet to solve the puzzle. In another video game, Kerbal Space Program, there is a small hill in the southern hemisphere of a planet called Duna, which transmits a monochrome SSTV image of 4 astronauts standing next to what is either the lunar lander from the Apollo missions, or an unfinished pyramid. Above them is the game's logo and 3 circles. It only emits the sound if an object touches the peak of the hill. A SSTV image was purported to be found on the radio in Grand Theft Auto 5. It was completely fake and should be a lesson to others looking for SSTV signals in video games.